Today we're going to look at lesson 5, which is titled Two Equations for Each Relationship. So we're going to work some more with equations for proportional relationships today, but now we're looking at two constants of proportionality, two equations. We're still representing the same proportional relationship. We're just looking at it from a different perspective. And that will really start to make sense as we move forward. For the warm-up today, it has a pattern shown to us here. And unfortunately, it did not copy very well on your handout. Seeing the colors hopefully makes a big difference here. But we've missed what the first figure looks like. We're shown what the second one looks like, skipping the third, and then we have the final figure, figure 4. So we need to identify what the first and the third figure would look like based on the pattern. So looking at what we can see in the pattern, it looks like we have a combination of blue and yellow rectangles here. And then it looks like they switch directions if you look at this figure as being kind of divided here through the middle. All right, I can also see figure 2 is kind of repeated here, and then there's a second one here. So it's almost like this has doubled into this. Now that would tell me that figure 1 is most likely half of this here. And if I look closely at the two images that we see, the first set has 2 blue on top, and it also does here. So I would imagine that all the figures are going to start the same way. That figure 1 would have 2 blue rectangles on top, and it would have 3 yellow rectangles on the bottom. That'd be figure 1. For figure 3, it's something between this. Since this has 2 sections, a left and a right, and this has 4, then figure 3 must only have 3 of those sections, and it's going to continue alternating just like we're seeing the pattern here. The only difference is figure 3 is going to be missing that final section that was added on figure 4. So here in the box would be what figure 3 would look like. All right, let's look at some proportional relationships. This says that 100 centimeters for every meter is the conversion that we're using. We did one similar to this earlier in the unit, but that might have been with meters and kilometers. So we're going to look at the tables. The first thing it asks us to find is the constant of proportionality for each table. Then it wants to know the relationship between the constant of proportionality. So I think it'd be best if we went ahead and filled in the table before we started looking at other information. So I can see here in the table that I have what's starting as a unit rate. And in my unit rate, if you remember, is my constant of proportionality. So my constant of proportionality is going to be 100, because 1 times 100 will give me that value equivalent to it in centimeters. Every quantity now, to keep a proportional relationship, must be multiplied by 100. And that's not something I need a calculator for. Multiplying by 100 is just going to increase the value of my number 10 times and then another 10 times. 10 times 10 is 100. Now that's just 2 place values. So this number, 94 hundredths, needs to get 2 place values larger, and it's going to be 94 when I multiply by 100, the constant of proportionality. 1 and 67 hundredths is now 167 centimeters. I'm going to continue that for the next one to get 5,724. And x is going to continue that pattern, but x can represent any quantity of meters. So whatever that value is, it makes no difference because this entire table was filled out the same way. I'm just going to make this value 100 times greater. by multiplying by 100. 100 times x. So we have the constant of proportionality for the first table. Let's look at the second table and fill that in. We're starting off with a ratio that is reversed to what was here. And if you look at our table is reversed. So they switched, and no longer are we starting with meters, we're starting with centimeters and working to meters. So if I'm in this first table getting 100 times larger when I go to a smaller measurement unit, here I'm going to a larger measurement unit. So I would imagine to be using a smaller number here in this table to use that larger measurement unit. And I can see here in this ratio that actually I'm getting 100 times smaller instead of 100 times larger. Now you might be thinking 100 divided by 100 equals 1, and you would be correct. That is correct. But since we're talking about proportional relationships, we need to be multiplying. So I'm going to have to multiply by a fraction. In order to decrease this value down to 1, I need a fraction. And anything like 100 times its reciprocal will give me 1. The reciprocal of 100 is 1/100th, 1 over 100. So if my constant of proportionality in this table is 1 over 100, that should bring all of these values down to 100 times smaller, or 2 place values smaller than what it was. So 250 will now be 2.5 if that amount is measured in meters instead of centimeters. If I continue that pattern, multiplying by 1 over 100, I would get these values in meters. And then finally, I need to continue this pattern for any quantity that I'm given in centimeters. If I'm given y centimeters, then I need to multiply it by 1/100th to decrease that number down to what it would be in meters. What is the relationship between these constant of proportionalities? Well, 100 and 1/100th are reciprocals. Finally, we're asked to write an equation. We're going to let x represent the measurement in meters and y represent the measurement in centimeters. So in this first table, if I was finding the number of centimeters, which we calculated here, y, if I was finding that number of centimeters, I would have to take the quantity in meters and multiply it by 100, just like we showed here. So 100 times x would give me that quantity here in centimeters. We had already done that here in this last section of the table. If I needed to write an equation for the other table, now remember, the direction of the columns, the location of the columns has switched. So if I was finding meters, which we said should be represented with x, then I would need to multiply 1/100th times y. And I just realized this should be a y here in this table, not an x, because that was the quantity we were given here. Okay, we're going to talk more about this in our next example. If we are filling a water cooler, it says Priya had taken 5 minutes to fill a cooler with 8 gallons of water from a faucet, flowing at a steady rate. So there we know we have a proportional relationship. The same amount of water is coming out of that faucet every minute. So we can set up a table, we can see this proportional relationship, and we can write an equation for it. It says to let W be the number of gallons of water after T minutes. So I believe this would be a great time to use a table. We're going to have time, or T, water, or W, and we need to just fill in the ratio that we're given, the rate that we're given. So 5 minutes time passes, 8 gallons of water goes into the cooler. 5 minutes, 8 gallons. Now that's not a unit rate, so that doesn't contain my constant of proportionality unless I do some more calculating, because a constant of proportionality would tell me how much water comes out of the faucet into the cooler every 1 minute. So that is simply just going to take a little division. Now the nice thing about fractions is they're representing division. So if 8 gallons of water flows out every 5 minutes, if I wanted to know how much water comes out every minute, I would take this total of 8 gallons and split it equally into those 5 separate minutes so I could see how much water is coming out each minute. Again, I could divide that, or I could just write 8 divided by 5, 8/5. Now that's an improper fraction, but it'll still work for our calculations. And if that makes you uncomfortable, I know how some people feel about fractions, then turn it into a decimal. 8 divided by 5 is 1.6, 1 6/10. So we have the unit rate and the constant of proportionality here. Now the first question says, which of the following equations represents the relationship between W and T? Select all that apply. All right, so there must be more than one answer here, or it's possible. Now, if I were to make an equation for what we just created here in the table, I just found my constant of proportionality is 1.6, or 8/5. Now I don't see 8/5 used in any of these, so let's go with 1.6. I see A and C are both using 1.6 as that K value. Remember that equation that we were using earlier was Y equals K times X. That's kind of our model for what the equation should look like, and K is our constant of proportionality. So if I have a closer look at my table, every amount of time, T, is being multiplied by my constant of proportionality to get W, the amount of water. That would mean this equation here is representing that. I'm going to take 1.6 times T times my time to get the amount of water, to equal the amount of water going in. Now, I need to be really careful that I don't have another answer choice here because it said select all that apply. So if I look at the other similar equation here, the only difference is the variables have switched places. If I take 1.6 times the amount of water, will that equal the time? Well, that would be an example here with the ratio that we're given. If I take 1.6 times 8, W, the water here, will it equal 5? Absolutely not. So this equation will not work using that constant of proportionality. But I do see that they've added a different constant of proportionality for choice B and D, 0.625. Well, if I had created a table going the other way and compared water to time, that would have switched the way that I wrote in my initial ratio of 5 minutes to 8 gallons of water. If I wrote 5 minutes here and 8 gallons of water here, this is going to represent a different constant of proportionality because something times 8 will give me 5. So what I'm finding by doing this now is not what we found in the first table. In the first table, we found how much water goes out of the faucet every minute. Here, in the other table, I'm finding how much time does it take for 1 gallon of water to come out of the faucet. I can do that calculation too. So by taking the 5 minutes of time, dividing it by the 8 gallons of water that came out, 5 divided by 8, or 5/8, that tells me how much of a minute it would take for 1 gallon of water to leave the faucet, 5/8 of a minute. We might want to look at that as a decimal though, because we're working in decimals in our equations. So 5 divided by 8 is 0.625. This is also considered a constant of proportionality depending on how we look at the problem. One constant of proportionality tells us how much water comes out of the faucet every minute. This constant of proportionality tells us how long it takes, how many minutes it takes for 1 gallon of water to leave the faucet. Okay, so we've answered these two questions now, but let's look quickly at what would be the best way to write this. Remember, we're multiplying our water times 0.625. So which equation is multiplying W, the water, times 0.625? It's right here. And that's going to equal the time it would take for all that water to enter the cooler, to leave the faucet and enter the cooler. So again, 1.6 is the amount of water per minute. Every minute, how much water comes out. 0.625 is how much time it takes for 1 gallon of water to leave the faucet. Okay, finally, we are going to look at the flight of the albatross. It's a large bird that can fly 400 kilometers in 8 hours at a constant speed. So that speed's not changing, therefore we have a proportional relationship to work with. It tells us to use d for the distance, t for the number of hours. So d for distance in kilometers, t for the hours of time. And an equation that represents the situation is d equals 50t, 50 times t. They're already giving us the equation here. So the first question, what are two constants of proportionality for the relationship between distance in kilometers and number of hours? Going back to our tables here in the last example, we found two constants of proportionality. Now it's not easy to see this way when they are decimal numbers, but as fractions, can you see those constants of proportionalities are reciprocals of one another? 5/8, 8/5. Now let's look here. I know, looking at this equation, this value here is going to be one of the constants of proportionality, just because of the way the equation should be set up. Y equals k times x gives me my constant of proportionality there. So I already know that. One constant of proportionality here is going to be 50. Now, based on the last example, it seems like the constant of proportionality, the other constant of proportionality would be the reciprocal of this. The reciprocal of 50 is going to be 1/50th, 1 over 50. So based on that, that's what I believe it would be. But now let's check. In order to get 50, the constant of proportionality here, using the ratio that we're given, 400 kilometers in 8 hours, if I write that ratio out and simplify it, 400 kilometers in 8 hours, if I wanted to find a unit rate for this, I would divide 400 by 8. And 400 divided by 8 equals 50. That's 50, and if I keep the same way that the unit of measurements are shown, that'd be 50 kilometers every hour, every 1 hour, because remember that comes from a unit rate. So kilometers per hour. All right, that sounds like a speed to me. So we have the speed of the albatross, that constant speed is 50 kilometers per hour, but now let's look at it differently. Here I have 1 over 50. Let me try a different color here. If I were to reverse the direction of this ratio like we did in the tables on the last question. And if I were to write 8 hours over 400 kilometers, so I've taken this ratio and written it the other direction. If I divide this, 8 divided by 400, or I simplify it, thinking like a fraction, 8 over 400 simplified, it's going to equal 1 over 50, 1/50th. And now that's hours per 50. I'm sorry. That would be 1/50th of an hour. Sorry, let me change this here. It would be 1/50th of an hour per kilometer. So that albatross is flying 1/50th, is flying 1 kilometer in 1/50th of an hour, a part of an hour, a very small part of an hour. So just over a minute's time. So what relationship is there between these two constants of proportionality? We have a speed of 50 kilometers per hour, or we have a constant of proportionality, 1/50th of an hour per 1 kilometer. Well, those numbers are most certainly reciprocals again. And if we had to write equations for them, we were given the one equation here, which would be the more common equation that we would use, being that we would most likely use this and this constant of proportionality. But if we did want to use it the other way, then our equation is going to be using the constant of proportionality 1/50th. And in this case, the way that the variables appear here, where we find the distance by multiplying the time and the constant of proportionality, is going to change. Now what we're going to do is we're going to multiply the constant of proportionality times the distance to equal the time. So it reverses those variables, because if you think of that table, instead of working one direction, we're working the other, and we're working with the variable here on the other side of the table to get back where we started. We're using its reciprocal to go back where we came from. All right, I hope this helps. Please remember, I am on Zoom all throughout the day to answer your questions. I'll happily go over any of your practice problems or anything from the lesson that you're unclear about. And we will take a look at lesson 6 tomorrow before we have the quiz at the end of the week. Everyone have a great day.